Damn quit saying relativity stinks, eclipses, orovsos, curves, no. It just shies starlight around a round celestial planet, the moon.
Everyone thinks a solar eclipse proves Einstein's curved space-time. They're wrong. That dark disk blocking the sun, that's just the moon. Physically, in the way, it's called geometric occultation. The moon's spherical body simply interrupts the light traveling from the sun to your eyes. No warped space, no relativity, just a rock in the road. Now, gravitational lensing is real. During an eclipse, starlight passing near the sun does bend slightly, just as Einstein predicted, but you cannot see that with your naked eye. It takes precise astronomical instruments to detect the tiny shift in a star's apparent position. The crisp, round shadow you're watching, that's pure spherical geometry, nothing more. And here's the thing, general relativity is over 100 years old. Some physicists are already asking, is it really the whole story? Something to think about.
A total solar eclipse is a purely geometric alignment rather than an effect of curved space. During an eclipse, three celestial bodies, the sun, the moon, and Earth, happen to line up in a straight line in our line of sight. Direct alignment. The moon passes directly between the sun and Earth, casting its shadow on our planet. Apparent size. Match. Because the sun is about 400 times larger than the moon, but also roughly 400 times farther away, they appear almost identical in size from our perspective on Earth. The blocking effect. The dark silhouette of the spherical moon simply physically blocks the direct light emitted by the spherical sun behind it, creating the glowing corona visible during totality. While Albert Einstein's theory of general relativity does state that massive objects like the sun curve space, causing starlight to bend slightly around it during an eclipse, the dark disk you see blocking the sun is just the physical shadow and body of the moon passing in front of it.
What if space doesn't curve? What if reality is an infinitely structured, perfectly flat medium with a flat line density of zero? Positive particles, negative particles settle into a raised, anchored equilibrium. Big claim, I know, but let me show you why. This idea is so compelling and where it runs into today's evidence. Start with the foundation. All things are particles first. Imagine the universe as a flat, endless canvas with zero background density. Particles find a stationary balance point instead of drifting like tiny tent pegs anchoring a taut sheet. That sheet isn't curving, it's flat, but its infinite structure lets matter lock into place. Now add a twist, 0-point gravity, not gravity from bending space-time, but gravity as a deepened ground state, an ever-present floor of energy that gives particles their stick. When enough particles anchor, they form atoms, stars, galaxies. Celestials seem to move, but here they're stabilized by anchored mass, guided by dominant suns, guided by galactic hubs, like beads sliding along invisible rails laid by equilibrium itself. Sounds neat. So why do most physicists say space curves? Because Einstein's general relativity explains a lot really well. Gravitational lensing bends starlight around galaxies exactly as curved spacetime predicts. Gravitational waves, ripples we've recorded, match the math of massive objects warping spacetime. GPS works only after we correct for time dilation from both speed and gravity, and black holes from their shadows to their mergers behave like geometry gone extreme. So here's the reframe. If space is truly flat and infinitely structured, a rival model must reproduce all of that. It has to explain lensing without curvature. It must predict time dilation, orbital precession, gravitational waves, cosmic microwave background. Could it? Maybe, if flat doesn't mean featureless. Picture a flat medium with hidden microstructure. Rules that make light change direction near mass, not because space bends, but because the medium's equilibrium shifts. Time could tick differently where the ground state deepens. Waves could emerge as collective oscillations of that medium. If the equations match the data, the story stands a chance. Where would I push this next? Derive lensing angles from equilibrium gradients, recover gravitational redshift and time dilation from 0-point depth, simulate galaxy rotation without dark matter, or show how the medium mimics it. Predict something new we can test soon. Space curving is the reigning champion for a reason. It wins on predictions. But bold ideas sharpen science. If space is a flat, zero-density stage with anchored particles in a deep ground state, the proof lives in precise math and hard tests. Until then, I'll keep asking the question, is gravity geometry or equilibrium? And I'll let the universe answer.
What if space doesn't curve at all? Imagine an infinitely structured, perfectly flat medium with zero density. Positive particles, negative particles holding matter in a stationary raised equilibrium. Celestials anchored in 0-point mass, guided by dominant sun's galactic bulk. It's a bold idea, so let me test it. First, the claim in plain words: space is flat, not curved. All things are particles first. 0-point gravity is the deep bedrock, stars, planets, galaxies. Here's the problem. Nature keeps handing me receipts for curvature. Start with light. If space were a flat medium, starlight would travel straight. During solar eclipses, we see gravitational lensing. Starlight bent passing the sun. Galaxies lens background galaxies into arcs, Einstein rings. A flat anchor model has to explain the same precise bending without curved space-time. Time next. GPS works only because satellites experience different rates of time. Speed, altitude, and Earth's gravitational field. Engineers correct for this every day. Curvature of spacetime nails those numbers. A flat stationary equilibrium must reproduce the same clock shifts, special gravitational time dilation, or it breaks your maps. Ripples in reality? In 2015, LIGO caught gravitational waves. Two black holes merged and spacetime itself rang. The frequency sweep matched curved spacetime predictions down to fractions of a millisecond. If space is a rigid, flat medium, what's waving, and why does it obey the math of general relativity so perfectly? Orbits don't just go round, they precess. Mercury's extra 43 arcseconds per century baffled Newton, but falls out naturally from curvature. Radar signals passing near the sun arrive late, the Shapiro delay. Even Earth's spinning mass slightly drags spacetime. Satellites measured that frame dragging with gravity probe B. What about particles first and 0-point energy? Quantum fields do have 0-point energy. It's real. Lensing angles, time dilations, waveforms, precessions, delays, extraordinary claims need extraordinary calculations. Now the universe does look nearly flat on the largest scales. Cosmic microwave background maps show that. But globally close to flat is not no curvature anywhere. Massive bodies curve spacetime locally, and that local curvature is what we measure, constantly. I love provocative ideas. They push me to check assumptions, but a good model does more than sound elegant. It survives contact with data. So if space truly doesn't curve, show me the equations that hit all these observations within error bars. Until then, the curves have it.
Reevaluate using the quanta physics theory using E, Ries MC2. Evaluating the equation E, Ries MC2 through the lens of quantum physics, quantum mechanics and quantum field theory, fundamentally shifts the interpretation away from classical mechanics or macro-scale spacetime. 1. Quantum vacuum and negative energy states, Dirac equation. The Dirac precedent. In quantum mechanics, Paul Dirac sought to unify quantum theory with special relativity, leading to the Dirac equation. This required solving for relativistic energy states, which naturally yielded a quadratic equation resulting in both positive and negative energy solutions. E minus plus P2 C2 plus M2 C4. The negative sign, meaning, in standard quantum theory, negative energy states, MC2, originally implied that electrons could endlessly cascade into lower and lower energy states, making the universe unstable. Dirac resolved this via the Dirac-C hypothesis, proposing that all negative energy states are already filled. Antimatter interpretation. In modern quantum field theory, those negative energy tau at mass states are reinterpreted using field operators via charge conjugation. They correspond to real positive energy antiparticles, like positrons, moving forward in time, or mathematical descriptions of particles traveling backward in time. 2. Quantum fluctuations and Casimir energy. Zero-point energy. Quantum physics dictates that empty space is never truly empty. It is filled with quantum vacuum fluctuations. Local negative energy density, under specific quantum conditions such as the Casimir effect, where conductive plates restrict virtual particle wavelengths, the local energy density of the vacuum drops below the baseline of free space, yielding effective negative local energy densities. In this quantum framework, a localized expression resembling E-mc2, or negative mass energy equivalence, describes boundary condition anomalies, virtual particle pressures, and localized quantum debt relative to the standard vacuum ground state. 3. Quantum field theory versus planetary. Relativity, microscopic versus macroscopic. Quantum physics operates strictly at atomic and subatomic scales, where probabilistic wave functions govern reality. It rejects the smooth, continuous geometry of Einstein's macroscopic general relativity. Renormalization of mass. In quantum field theory, the bare mass m of a particle is heavily modified by interactions with quantum fields, like the Higgs field. The effective mass observed can fluctuate. If an isolated system or virtual interaction evaluates to a negative energy eigenvalue, it represents a transient quantum state rather than a permanent planetary feature. Summary of the quantum reevaluation.
Damn quit saying relativity stinks, eclipses, or rove sos, curves, no. It just shies starlight around a round celestial planet. The moon.
Everyone thinks a solar eclipse proves Einstein's curved space-time. They're wrong. That dark disk blocking the sun, that's just the moon. Physically, in the way, it's called geometric occultation. The moon's spherical body simply interrupts the light traveling from the sun to your eyes. No warped space, no relativity, just a rock in the road. Now, gravitational lensing is real. During an eclipse, starlight passing near the sun does bend slightly, just as Einstein predicted. But you cannot see that with your naked eye. It takes precise astronomical instruments to detect the tiny shift in a star's apparent position. The crisp, round shadow you're watching, that's pure spherical geometry, nothing more. And here's the thing, general relativity is over 100 years old. Some physicists are already asking, is it really the whole story? Something to think about.
A total solar eclipse is a purely geometric alignment rather than an effect of curved space. During an eclipse, three celestial bodies, the Sun, the Moon, and Earth, happen to line up in a straight line in our line of sight, direct alignment. The Moon passes directly between the Sun and Earth, casting its shadow on our planet. Apparent size. Match. Because the Sun is about 400 times larger than the Moon, but also roughly 400 times farther away, they appear almost identical in size from our perspective on Earth. The blocking effect. The dark silhouette of the spherical Moon simply physically blocks the direct light emitted by the spherical Sun behind it, creating the glowing corona visible during totality. While Albert Einstein's theory of general relativity does state that massive objects like the Sun curve space, causing starlight to bend slightly around it during an eclipse, the dark disk you see blocking the Sun is just the physical shadow and body of the Moon passing in front of it.